Welcome back to ECE 320A. In this video, before we get started, this is going to overview three-phase power, but for announcements again, with three-phase power, we're in Chapter 11. Last time we talked about the characteristics of three-phase power. Now let's get a little bit more detailed in terms of what that might mean relative to our sources and our loads, what those structures might look like, and that will help you complete homework number 3, which homework 3, homework 4, and homework 5 will be the content for exam number 2, which will happen after unit number 5. Today, what we want to do is work through this high-level view, again, of three-phase power. We'll start with a high-level block diagram, which we showed last time, but we also now want to look at how are these different pieces connected or structured. What's the balanced phase sequence? What does that mean in these systems? We can have one or the other. We can have an ABC, which is also called a positive phase sequence, or we could have an ACB, which is called a negative phase sequence. We'll illustrate what that means and how the different voltages are related in the A phase, the B phase, and the C phase. Remember, we have a three-phase system, and now we simply classify those as an A phase, a B phase, and a C phase. We will also then look at how a source and or a load are connected, be those in a Y configuration or a delta configuration. We could have a Y that's a positive phase sequence or a Y that's a negative, or we could have a delta that's a positive or negative. So the phase sequence is different from the interconnection structure or the connection structure. And then in the subsequent video, we will talk about how we interconnect sources and loads, and we might actually hint at that or illustrate what that means in terms of pairing these up at the end of this lecture. Here is a high-level view or a block diagram of a three-phase system. And you can think back at that graphic that we had in the last video. We have typically our sources are on the left and our loads are on the right. It's just now that we have three phases. We have an ABC phase for our source. We have an ABC phase on the load, and we have transformers. You know where those are. Those are right at the source and right at the load, and we have transmission lines that connect the source and the load. WLOG, or without loss of generality, we will be neglecting in this class the transformer part of that process or of this system. So we won't worry so much about stepping up or stepping down the voltages. We will just play with the source and the load interconnected with transmission lines, and our transmission lines a lot of times might have impedances associated with those, but the idea now is we have three phases at both the source side and the load side. Now, those three phases can come in two different varieties. We can have a positive phase sequence or an ABC phase sequence, or we can have a negative phase sequence. Let's talk now about the positive phase sequence. In a positive phase sequence, and it's balanced, again, we have several things going on. We have balanced, and we have a phase sequence. For a balanced three-phase sequence of voltages, we have an A phase, a B phase, and a C phase. The A phase, let's just say that's our reference phasor, and we'll let that have an angle of 0 degrees. Then relative to that A phase, in the positive phase sequence, we have a B phase and then a C phase. The B phase has the same, and this is balanced, which means that the amplitudes are the same. The angles are just separated by 120 degrees. Pictorially, if we sketch those three vectors, the A phase vector, the B phase vector, and these lengths are supposed to be, of these arrows are supposed to be the same, and they're supposed to be now separated by 120 degrees. The B phase is now 120 degrees behind the A phase, and the C phase is 120 degrees behind the B phase, but typically we try to keep these angles less than 180 degrees. So minus 240 degrees is equivalent to plus 120 degrees. So we can get to this location either by going all the way around to minus 240 or to plus 120. And to keep the angles between plus and minus 180, we'll typically just say the C phase in a positive phase sequence. When the A phase is at 0 and it's balanced, then the C phase will have a phase of 120 degrees. And a way to maybe think about this positive phase sequence is, if I can now try to illustrate my lack of artistic talent, you could envision sitting right here and watching these different phases. We have actually a counterclockwise rotation happening. So this A phase, again, we're in sinusoidal steady state. These are rotating around at omega radians per second. The angle is just where they are relative to each other. But at any particular instant of time, the A phase might be somewhere else in this circle, but wherever it is, 120 degrees behind it is the B phase, and 120 degrees behind the C phase, behind the B phase is the C phase. But if you're now sitting here and you have, this is your eyeball, then what are you going to see? Well, you're going to see the A phase, then a little bit later you'll see the B phase, and a little bit later you'll see the C phase. So that now gives us this positive phase sequence. If you forget where B and C are, then just think of positive as the typical way of saying your ABCs. It's ABC in that order. Then you can very quickly sketch this diagram and say, oh, here's my A phase, B, C. If I was sitting here and it was spinning in a counterclockwise rotation, which of these phasors will I see next? So I'll first see the A phase, then the B phase, and then the C phase, and that's a positive phase sequence. Now I think you can anticipate what's going to happen if we change this and say we have a negative phase sequence. Now, if we have a negative phase sequence, again, we have the three phases, A, B, and C. But now, the negative phase sequence is not the typical way that we say our ABCs. It's now ACB. So it's the negative of what we're used to seeing. So now, when we are sitting here and we were looking from our vantage point, and this is now going in a counterclockwise rotation, in a negative phase sequence, we're going to see A, C, then B. And for that reason, then, if A phase is our reference phasor again at 0 degrees, then the next phase that we will see is the C phase. So the C phase has the same amplitude, V sub m. It's now at minus 120. The B phase is behind the C phase 120 degrees. So it's now 240 behind the A phase, or it's at 120 degrees ahead of the A phase. But if we are sitting here watching this with our eye, this rotating around, then we will see the A phase, then the C phase, and the B phase, or this is now the negative phase sequence. The significance of the A, B, and C, or I'm sorry, we have three phases, but the significance of keeping track of whether we have a positive phase sequence or a negative phase sequence, we can't be connecting these up together. So that's why I have this yellow caution light with red letters saying if you're dealing with these circuits, you cannot have them operating in a connected fashion. And so now you've connected up the A phase, the B phase, and the C phases together, or they're now in parallel. You can only operate these circuits if they have or share the same phase sequence. You can't have a positive phase sequence interconnected with a negative phase sequence. So the phase sequence is different from what we will talk about in a little bit, which is a Y connection and a delta connection for either a source or a load. But right now, the phase sequence being positive or negative is this particular relationship between the A phase, the B phase, and the C phase. If it's positive, then we have A, B, C. B is 120 behind A, C is 120 behind B. No matter where they start, they're always 120 degrees different. So if the A phase was actually at 30 degrees, then the B phase would be 120 behind that 30 degrees, or the B phase would now be at minus 90 degrees. And the C phase would be similarly located, 120 degrees behind that B phase. So now we would be at 150 degrees if we wanted to keep our angles between 180 plus and minus 180 degrees. The C phase, if the A phase was at 30 degrees, the C phase would be 120 degrees ahead of that effectively, or at 150 degrees. Convert, or in contrast to that, if we had the negative phase sequence, if it's balanced, they all share the same amplitude. It's just that the angles and the way that they are oriented one to the other is different. In the C phase, we have A, C, B, and so the C phase is 120 behind the A phase, and the B phase is 120 degrees behind the C phase. That's the phase sequence, and I want you to make sure that that is understood, and that's different from what we will talk about now, which is how the sources and the loads could actually be interconnected internal to this three-phase system. And to get us thinking about that, I could ask you the following question. What is, if I added up V sub A with V sub B, and these are now phasors, if I added these up, the A phase, the B phase, and the C phase, what would I actually end up with? If I now added up the A phase vector, which now we can say that that's, let's say right here, this is now V sub A. Suppose now I added to that head of that vector V sub B, and let's just, for grins, let's pick the positive phase sequence. So now I add to that the B phase vector, the tail of the B phase to the head of the A phase. Then I would come down here, and now I want to add the C phase to that, and I hope that now you can see that if we have a balanced three-phase system, which means the lengths are all the same, it's just the angles are different, then if I wanted to know what's the sum of these three phasors, the A phase, the B phase, and the C phase, then that sums to 0, because I start here and I go A, B, and C, and I get back to where I started. In this phasor form, I have 0. Well, what does that actually say? Or can we say anything more than that? In fact, we can. If I now had the instantaneous value of the A phase voltage V sub A of t as a time domain waveform. It has an amplitude of V sub m and it has a phase of, let's say, 0 degrees, and it's oscillating at a frequency of omega, 377 radians per second. If I now add that to the B phase, instantaneous values of voltage, and the C phase, that likewise will be 0. So as these three voltages are spinning around in time, if we added those three up at any instant in time, instantaneous value is going to be 0. And we'll use this. So this is sort of to be used, so keep this in your memory bank, will be used to justify our application of single-phase equivalent circuits in solving balanced three-phase circuits. So don't forget this particular condition, that the sum of the three phases, if it's in a balanced configuration, will sum to 0. And that means that instantaneously, if we are adding up instantaneously these three voltages, they will sum to 0. Now, what we want to talk about is the way that we connect these sources, the A phase, the B phase, and the C phase, in your source network, and then we'll talk about the load network. We're going to show the two different ways that we can wire a three-phase set of voltage sources. And what does that look like? Well, now we can say that we have one configuration. Let's say this is now our A phase. And we now have a B phase. So this is now the A phase, and we also have a C phase. And notice all of the negative terminals of those generators are connected to each other. And if we wanted to, then we could say that here is our source, and we have three terminals of that source. We have an A terminal, a B terminal, and a C terminal. And in this particular configuration, which I hope you see maybe an upside down Y if you looked at it this way, well, this configuration is what we call the Y configuration of our sources. And in fact, we could have, because there's a neutral terminal in common to the way that we've interconnected these generators, these could actually have a neutral conductor that could be pulled out from this interconnected source configuration. So now this is the Y configuration. If I say we have a Y configured source, and in this particular case, I haven't shown some internal impedances of those, but if I did, those impedances could be introduced into this particular source network where I've sketched those boxes. And the impedances would be maybe some resistance and some inductance associated with each of those phases. And if we're in a balanced system, V sub A, V sub B, and V sub C will look like the balanced three-phase circuit or set of voltages that we just talked about. And these generator or source impedances, let's say capital Z, G for generator A phase, Z sub generator B phase, and Z sub generator C phase, if it's balanced, those will all three be the same. That's one way to wire up a three-phase set of generators or sources. That can be contrasted with the following. Let's say now we have an A phase here, and connected to that, we now are connecting the negative terminal of that A phase to the B phase, and connected to the negative terminal of the B phase is our C phase. And we can now associate with each of these positive terminals and if we now looked at this as a, I won't say a black box, I'll say a yellow box, now we might not be able to determine what's going on inside this yellow box. We have an A, a B, and a C terminal, and we have an A, B, and a C terminal here. But this particular internal configuration is now more like a triangle or a delta, and this is now our delta configuration. That is one of the two different ways that we will introduce a connection or a wiring structure on the source side of our system. And again, if we wanted to introduce generator impedances, then we would put those into this particular location of the A phase, the B phase, and the C phase. And you can now see how these are connected. It's minus, plus, minus, plus, minus, plus all the way around that delta, with the plus terminal corresponding to the particular phase source of that particular terminal. Meaning here is our A phase, and here's the positive terminal of that, and so that's now our A phase terminal coming out of our yellow box. What I am indicating with those with the blue boxes is this, I actually drew those without what's internal to those blue boxes, which could be generator impedances, where the generator impedance inside the blue box might be represented by a resistance, let's say a winding resistance. If that source is now some generator, then that generator has some wiring associated with it, and we now have resistance of that wire, and we also have these coils, so we have some inductance that also is a part of each of those phases impedance at the source. So we have some inductive reactance. And this would then say something like Z sub G and fill in the blank, either the A phase, the B phase, or the C phase. We now have R sub W plus J X sub W. And if we have a balanced configuration, then each of these phases in our generator will have the equivalent winding resistance and inductive reactance in each of the different phases. That's how we can wire sources in our three-phase system. Let's now look at the other side of this, the other side now being the right side in this block diagram. We've just talked about the source side on the left. Now let's see how we can wire up the load side, and consistent with how we have wired the sources, the loads can also be either wired to be a Y or a delta. If we put them in a delta connection, We'll do that second since I'm saying Y first. So let's look at the Y. In the Y, we typically draw it maybe to not look quite so Y-ish, but hopefully you can see the Y characteristic of this. And now let's just say this is our A phase impedance, this is our B phase impedance. And notice, I hope, in the source I had lowercase letters corresponding to the phases. Now I'm switching in the load side to have capital subscripts labeling the different impedances and terminals. And the C might be a little bit difficult, but hopefully by context you'll know whether that's lowercase or uppercase as far as a letter. And this is now the Y connection structure of a load. Hopefully you can see the Y part of that. The delta configured load is going to now, let me put the A phase here, impedance. And let's now, the way that's written, let's say that this is now the A terminal of that impedance. Connected to that is the B phase load, and connected to the B is the C phase. And now we have hopefully illustrated the two different wiring strategies for interconnecting the loads. We have the Y with Z sub A, and if these are balanced, then Z sub A is identical to Z sub B is identical to Z sub C as far as impedances are concerned. Likewise in the delta. Now, if we have two different ways of connecting sources, and we have two load connections, I hope that it's clear that by combining those in any particular way, we end up with four possible arrangements for connecting sources to load. Or I might call this interconnections, meaning for the source and then the load or loads, then we could have, for the source, we could have a Y connection structure, and we could connect that via transmission lines to a Y connected set of loads. Or we could start with a Y source and connect that with a delta connected set of loads. And we have the other two possibilities for sources connected as deltas. If our source now was starting as a delta, or will be in a delta, maybe it's connected to a Y load, or maybe we have a delta source connected to a delta load, and those now give us the four different possible arrangements or interconnection structures, which we will pick up with next time and try to analyze those, because now these are interconnected with transmission lines, and we want to be able to perform the analysis on any of these four possible interconnection structures.